Okay, in geometry, a tangent line is one that touches a circle or a curve of any kind, actually, in only one point. And that would be like the red line that's shown in this figure. You should have that same figure in your notes, it's just that your notes are not in color. So intuitively, if you think it can only touch it in one point, that it indicates the direction of the curve, because it only touches it in that one place. And when it indicates the direction of the curve, if you think about direction as being positive or negative, and how steeply positive or negative, then that's the same as a slope. Okay? So one of the things that we're going to have to do for this to make any sense is we're going to have to make sure that you understand what a tangent line is, because we're going to talk about them so much. So on this drawing, the lines through points P1 and P3, here and here, are actually tangent lines, because they touch the curve in only one point and not any of the adjacent points. The lines through P2, while they only touch the curve, the line at P2 only touches the curve in one place, and of P5 only touching in one place, but they are not tangent lines because they are cutting through the curve. They don't tell you anything about the direction of the curve at that point. What about P4? What do you think about P4? Is it or is it not a tangent line? Does it only touch in one place? If we could home in on it, we might be able to see that it might only touch it in one place. But the problem that probably bothers all of us is that it doesn't seem to touch the curve and take off again, because it appears to cut through the curve. But now here's the second question. Okay, so it touches it in one point, maybe. But in order to be a tangent line, it has to also show the direction of the curve. Does it do that? Does it give you an idea of the steepness of the curve? And for that, I would say yes, it probably does. But it is questionable, because it still cuts through the curve. So it makes you kind of doubtful. And that's because point P4 is a very special place on that curve. It's called an inflection point. Okay? And tangents at inflection points can touch it and move on, because the curve itself at that instant inflection point actually for just an instant becomes straight before it stops increasing so fast and starts to decrease. So P4 is kind of a special case. So we're going to have to define a tangent line more carefully to decide whether P4, whether the line at P4 is in fact a tangent line or not. So first thing we're going to do is we're going to try to figure out how to relate tangent lines and secant lines. So if you wanted to find the slope of a line tangent to the graph of a function at a given point, you can choose R, which is down here at the bottom of the curve, to be a point with the coordinates A and F of A, and a different point S with the coordinates A plus H and F of A plus H, and that's called a secant line. Now notice we're not talking about limits here in H approaching 0. We're just basically saying here that the difference in the X values of R and S is H. And the difference in the Y values of R and S is whatever the difference F of A and F of A plus H are. So basically, it's still just the difference in two y values. So we're not talking about limiting it, because obviously here h is not 0. So h is actually just the difference between 2 points in both their coordinates. It's the distance apart they are, if you want to think of it that way. Now, by the definition of slope, the slope of line RS is change in y over change in x, which is f of a subtracted from f of a plus h, because f of a plus h is bigger, and a subtracted from a plus h, because again, a plus h is bigger, larger in magnitude. And since a plus h minus a leaves us with just h, then basically h is just the difference in the x values. And this slope corresponds to the average rate of change in y with respect to x over the interval from a to a plus h. Now, all of that really is just a review of what we talked about in the last section. The average rate of change is the slope of a secant line. Secant meaning that it touches the line in 2 places, not just one, or touches the curve in 2 points, not just one. So it's the average rate of change. As h gets really small, and we say it approaches 0 though, what happens is that the point S is going to slide closer and closer and closer and closer and closer to being on top of the point R, until S and R will have the same coordinates, which means h will have become 0. And at that point, S and R are equal to one another. Now, and when they're equal to one another, we can't calculate a slope by the usual methods, but we can calculate slope as h gets smaller and smaller, thinking of it as a limit. So as h approaches 0, the limit is the slope of the tangent line at point R. So in order to find the slope of a curve, you're actually looking for the slope of a line that's tangent to that curve, as the difference between the 2 points become 0, or they become on top of each other. This is an applet that I think might help you actually visualize that. And that link is live, by the way, in the PowerPoint that I posted for y'all. So what we're going to do here, the line in red passing through the 2 points, there's a large blue point and a similar point in sky blue, and then the graph of the function is in green, and the large blue point is the location of x, f of x. It's the one that's going to stay still. And you can change this point by dragging. So watch what happens as I drag that point closer and closer and closer to the other point. Now at this point they're still distinguishable, but the difference between them is very, very small. It's about 1/10. And the slope of that red line is about 0.7. Now if I get any closer, notice that 0.7 is not going to change a whole lot. Whoops, I actually grabbed the wrong one. Have to be careful to grab only one of them. Let me see if I can get the initial point at exactly 1/2. Ah, there. Yes, yes, that works. When they get close together, it's hard to grab just one of them. So as I let that get closer and closer and closer, what you see happening is that the denominator is shrinking closer and closer and closer to 0. But when I actually let them merge, it goes to undefined because we can't find slope with just one point. And I could actually go the other direction. You don't have to move the cyan point. You could actually have moved this one and put it somewhere else. So now if I want, trying to get it to where x of 0 is about 1. And if I move it, notice again, closer I get that other point, my slope gets closer and closer to actually being the slope of that tangent line. Those two are still 3 100ths from each other. Now I've got them at 2 100ths and at 1 100. Whoops. Yeah, you really can't keep them apart very long. They tend to want to stick together. So you can see that you can find something really close to the slope of the tangent line by doing that process. And that's a live link in the PowerPoint, so you'll be able to go back and play with this.
It doesn't work.
It,
The live link doesn't work.
okay, we can fix that. Let me see if this one works. Does the one at the bottom work for you?
No, I tried that.
You tried both of them?
You can get it if you right click and do open hyperlink.
Okay, yeah, if you right click it and do open hyperlink, it should open it. You're probably looking at it from D2L too, aren't you?
No, I downloaded it to PowerPoint
Okay.
to see if it works.
But if you play around with it, that may help you understand what that algebraic process we're doing is actually doing, is it's physically sliding the 2 points closer to each other. So the tangent line of the graph of y equals f of x at the point A, f of A, is the line through that point having the slope of f of A plus h minus f of A divided by h and take the limit as h approaches 0. If that limit exists, it may or may not exist. If the limit doesn't exist, then there is no tangent at that point. Now, if we look at it from that definition, let's go back a few. If you look at it from that definition, if you try to choose points close to P4 and slide them closer and closer to P4, does it converge on a limit as that distance gets smaller and smaller? Does that slope reach a constant? Looking at P4. If you take the limit, sneaking up on P4 from the left and sneaking up on P4 from the right, that's the y values, the change in the y values. So are you going to converge on some single value? Yeah. And at that last minute, before h is equal to 0, the difference between those 2 points that are sneaking up on the same value becomes the slope at that point. So by that definition, P4 is a tangent line because the limit from the right and the limit from the left approach the same value. So let's look at the graph of f of x equals x squared plus 2. We're going to find the slope in the equation of the secant line through the points x1 and x2, where x1 is equal to 1.
I don't know if it works out to be the same or not. The next few slides, everything changes to x equals -1. X equals 2.
That would be my fault. But I can fix it. I'm glad you noticed that. This is a new PowerPoint, and I had not had a chance for everybody to find errors yet.
We'll still want to find the slope equation for tangent line at point x equals -1,
Yeah, and I'm trying to find points x negative. No. Let me see where else we need to change it. At the point x equals -1. This should have said -1. That's what I was trying to find. So let me go through all of them and get them changed. Because I'm pretty sure that's the way the problem's being worked. You may have to correct your handout too, because I bet it's the same way. -1 and 2. Yeah, and it's supposed to be -1 because that's what the graph is. And then x equals -1. Okay, I think that fixed it. So let's try again and just watch carefully and make sure it fixed everything. So we're going to look at the graph of f of x equals x squared plus 2 and find, in part A, we're going to find the average rate of change, like we did last time in the last section. We've got 2 points. X is -1 and x is +2. And then we're going to find the slope in the equation of the tangent line at the point, so we're talking about instantaneous rate of change, at the point x equals -1. In other words, what we're really finding in part B is what is the slope of the curve at x equals -1. Just like lines have slope, curves also have slope, but they only have them at a single point. So we'll take part A first. If anybody notices anything out of order, let me know. So, find the slope and equation of the secant line. X is -1, x is 2. When this function has -1 plugged into it, then we're going to have -1 squared, which is 1 plus 2. And f of 2 should be 2 squared plus 2, which should be, this is 4 plus 2 is 6, and 1 plus 2 is 3, and 6 minus 3 is 3, and 2 minus -1 is 2 plus 1, so that's 3. So that slope is 1. That's the slope of the secant line. So the slope of the secant line through -1, 3 and 2, 6 is m equals 1. The slope is 1. And we can find the equation of that secant line by using the function form of a straight line, y equals mx plus b, because we know that one of the points, and it doesn't matter which point, we could use the 3 and the -1 and the 3, or we could use the 2 and the 6. But we're going to get the same equation either way. So I chose to use -1, 3, -1 being x, 3 being y, and the slope is 1. So 3 equals 1 times -1 is -1, and add 1 to both sides, we actually then get 3 plus 1 is equal to b. So if b is 4 and m is 1, then our line is y equals 1 times x plus 4, or y equals just x plus 4. Now, in order to verify that this actually looks like that, I'm going to escape here for a second, get the graphing calculator because it's handy. Go to the y equals menu, and we're going to graph x squared plus 2. And we're also going to graph this secant line, which is x plus 4. And so that we can see this really well, I'm going to go to the window, and I don't really think we need to go as far as from -10 to 10 because our points are only -1 and 2. So let's try -5 to 5. and then we'll just look at the graph. So there's your curve, and there's your secant line, okay? And if you want to verify that the intersection points are -1 and -1, 3 and 2, 6, then we can verify that by going second, trace, down to intersect, and hit enter 3 times. And it says one of the intersection points that's on both the curve and the line is -1, 3. And then if we want the other value, what we're going to need to do first is we're going to have to trace closer to it. So I'm going to get over close to it, and then I'm going to go second, trace, number 5, and hit enter 3 times. And it says the other point is in fact 2, 6. Okay, so that line does contain the points, that curve does contain those 2 points. You could have also verified it going to your graph and putting in -1 and 2 and see that those points are the same on both functions. So basically, this is a graph of the curve and its secant line, okay? Now, for those of you that are interested, and this is not an iPad app, be very happy about that. This is not an iPad app. In fact, as far as I know, this app hasn't ever been made into an iPad app. This is an app I've been using on a computer for a long time. And if you don't like graphing stuff and not being able to print it out, like, you know, you graph it on your calculator, but then you can't print it out and hand it in, and it would be helpful to be able to print it out and hand it in. So this app is actually from a company called Ksoft, and I'll show you how you can get it. And it's shareware, so you can use it for 30 days, 60 days to try it out and see if you like it. And if you don't like it, then you just don't buy it and you delete it. But all you have to do is do a search for Graphmatica. Free download. And it will take you right to it. So you just start your download. You don't want, wait.
You searched the internet, not that website.
Yeah, I don't want that particular website. Let me back up. Okay, here we go. Yes, this looks more like what I'm used to seeing. Download Mathematica 2.4 for Windows 846 kilobytes. So you click the download button, and you'll want to save the file and then extract it and run it on your computer. I think I can still do that on this computer. We're going to find out. I didn't think it was on here. It is. So I can launch Graphmatica from here. Now, you can choose the way this looks. I'll let you play around with it. You don't have to download. This is just something that I think might be helpful to you. On your tools, on your graph paper setting, options, graph paper. You have options for different kinds of graph paper, and you can change colors. You can have a black and white graph. You can have one that has, it's a white background with colored lines, which I like because it prints out real well. And then you can graph y equals x to the second plus 2. And then you can change your grid range . I'm sorry, that's a view, that's not an option. Change your grid range to whatever you want to. You don't have to go from -8 to 8. You can go from -5 to 8. So you can change all of those any way you want to until you get your graph the way you want it. Let's go up to 10. So there's your graph. And then if you want to add the secant line, y equals x plus 4, and it'll draw the secant line for you. You can find the intersection. And you're gonna, what you do on this one is you guess at where you think the intersection might be, and we think it might be at -1. Oh, it says guess for an off screen. Okay, just calculate it for me then. Okay, and there it shows you both intersections. It doesn't label them for you, but it will tell you what they are. So it's a useful little thing to have, and one of the things that it will do is it'll draw the tangent line for you, and we're going to want the tangent line here in a few minutes, so I'll wait and we'll come back and draw the tangent line. So let me escape from there and bring back the PowerPoint. But that's what I used to construct this graph. And as you can see, I've been able to annotate it and have it do all kinds of nice things. So that'll save you time when you're on a test or on a quiz. And I will allow you to use Graphmatica for anything that you want to use it for if you like it. So going back to example 1 now and talking about the tangent line, it says find the slope and equation of the tangent line at the point x equals -1. Okay? The slope of the tangent line at x equals -1. And again, I'm going to switch over to the overhead so I can work through it with you. Remember that our function is x squared plus 2. And the value of A, the point of tangency, is going to be -1. And what we're going to calculate is the limit as h approaches 0 of f of -1 plus h minus f of -1 all over -1 plus h minus h, which is going to be that numerator over just h. So we're going to calculate the slope of the tangent line. And the way that we're going to do that, f of 1 plus h for x squared equals, or x squared plus 2, -1 times -1 is 1 minus 2h plus h squared plus 2. And the 1 plus 2 is going to turn into 3 minus 2h plus h squared. And then f of -1 is -1 squared plus 2, which is 1 plus 2, which is the 3. So when we subtract these two, we're going to subtract 3, and this is what we're going to be left with. So we're going to take the limit as h approaches 0 of -2h plus h squared over h, which means we're going to factor out the h just like we did in the others. And the limit as h approaches 0 of -2 plus h is simply -2. So the slope of the tangent line is -2. And since we have y equals mx plus b, and we know that m is -2, and we have a point, and that point is -1, 3, then we can plug in and find b. So -2 times -1 is 2, and we're going to subtract 2 from both sides to get b, and 3 minus 2 is 1, so b is equal to 1. Our equation then the equation of the tangent line is y equals -2x plus 1. So if I go back to Graphmatica and I add another line, I indeed have a tangent line. And it does only touch at that one intersection point. And you could use the intersect tool. Let's see, and we want the intersection of the original function, which is the x squared function, and of -2x plus 1, and tell it to calculate for us, and it says that's at -1, 3. And here's the point -1, 3. Okay? Now you don't necessarily have to always calculate the slope, or no, I'm sorry, not the slope. You don't have to always calculate the tangent line itself or the secant line itself. But if you do, it's kind of helpful to be able to draw it on the graph and make sure that it is what you actually thought it was. And we can see here that that is actually what it is. And if you want to get rid of any of the lines, just so that you know how to do that in here, all you do is go back to view and tell it, let's see. No, I'm sorry, it's not view. It is edit. And you can actually delete all the graphs, delete a particular graph, or you can copy the graph or export the graph as a JPEG, a picture, or you can copy it as an enhanced color meta file. And any word processing program, let's see, let me find Word. The only problem in this class is it's hard to find Word because they don't put it on the menu.
If you look at the very bottom of what you're looking at, you can just search Microsoft Word. Go down to the little more of the mouse, right there.
Yeah.
Just Word, I think.
Actually, just Word should do it. Nope. Word, it brought up WordPad.
Unless something loaded, then it's, I've got Word on this computer, search for that.
Wonder how they manage that. Well, the other way that I'm just kind of roundabout doing it, so I can always go find a Word document. And then just open me up a new one. Because I just wanted to show you how you can copy and paste. So I've copied it and just hit paste, and you can paste it into a Word document and print it out if you want to. Or you can save it as a PDF and upload it to Shobi if you need it for a Shobi assignment. Which is a lot handier, I think, than the calculator in this case. Okay, but I think we've gone aside long enough. So we calculated and found the slope of the tangent line, the equation of the tangent line, and there is a graph, and this one comes out of the textbook, of the tangent and secant line for that problem. And that one is in your notes. But one of the things that I'm going to point out to you in the next slide is that if you look at a closer in view of your tangent line, you'll notice that the curve appears to be straightening out. And one of the things that we can see on the calculator about that is we can kind of see that. So I'm going to go to y equals on my calculator. And we've still got x squared plus 2 in there. Let's see, that, don't think that's our function. Yes, it is. That's our function still. Yes. And we've got the slope of the we've got the equation of the secant line, so we'll also get the equation of the tangent line, which was negative 2x. Plus 1, I think. We'll know in a minute. Yep, there it goes. So what I'm going to do is I'm going to go back over here. I'm not really interested in the secant line right now, so I'm going to turn it off. So all I see is the curve and the tangent line. The way you turn an equation off is just put your cursor on the equal sign and hit enter, and it'll turn it off. And what I want to do is I would like to look at a really more close-up picture of this part of the graph. So I'm going to start out doing it manually by going into my window and going from -3 to 0. And I only want to see in that top quadrant, so I don't need to see any negative x values, and I don't need to go up any higher than probably 4. So I've considerably narrowed down the window. And there comes your tangent line, okay? Now notice this part of the graph right here. Those two are so close in and around that point of tangency that on this viewing window, they appear to be actually touching in more than one point. What I'm going to do is I'm going to go to the value, second trace, and then choose value and tell it x equals 3, because I want to see that point of tangents, or x equals -1, I'm sorry, not 3. X equals -1, and hit enter. And what did you not like? Oh, you didn't like my subtraction sign, I'm sorry. So there's the point of tangency, okay? And we're going to do this several times so you can follow along with me and see it on your calculator. I'm now going to go to zoom and number 2, in. And I'm going to get that little cursor as close as I can to being exactly -1, but I may not be able to get it perfectly. That's pretty close. So I'm going to zoom in again by hitting enter. So there's the curve, there's the tangent line, okay? And if I type -1, no, it didn't work from there. Go back to my graph. Second trace, -1. Okay, there's the point of tangency. Zoom in, enter. You can only just barely see the difference between them now. I'm going to do one more time. Second trace, value, -1, zoom in. I'm just going to leave the cursor where it is and hit enter. There's the curve. There's the tangent line. Does the curve look like a straight line at this point? Yeah. Very, very straight line. So the slope of the tangent line and the slope of the curve are in fact the same at that point of tangency. And that's what I'm trying to show you, is that they do have the same slope. The process of the derivative is basically zooming in on that point. And it starts to look linear, so you actually know that the line and the tangent line and the curve have the same slope at that point. And it's easy to calculate the slope of the tangent line. Well, not, ridiculously easy, but with arithmetic you can do it. Now, I told you could leave these off of the test, but this is something that is useful to know, so I'm going to show you how to do it. If I want to use the graphing calculator to find the slope of the curve at x equals 1, and this says f of x equals x to the x, I'm going to do it with the curve we've got and show you how to actually do this. We're going to go back to y equals, I'm going to get rid of the secant line and the tangent line, okay? Because we know what that tangent is, we know what its slope is. I'm going to use calculus, but I need to get back to a window that actually worked well, so I'm going to go back to -3 to 3, and from -3 to 3, let's see what that looks like. Yeah, I want it a little bit taller. Let's go to 6. Ah, wrong value, sorry. Now what I want to do is I want to go to y equals. Make sure that I've got the function in right. Then go to the home screen, clear it off, and press your math key. Okay? Scroll down until you see number 8. Choose number 8. Now, those of you that have an 84, this looks different from what mine does. Okay? And your entries are going to be a little bit different. Let me see if I can, I think I put a slide in there to show you the other entries. I'll just have to show you how to do it, and then I'll have to come help the people that have the 84. The first thing that the 84 people are going to enter is going to be the value that you want the derivative with respect to, which is x. But for the 83 people, the first thing you enter is the function. Now, since I've got it in y1, I can simply use y1. But if you don't already have it in y1, you can actually type it right here. And let's see, that original problem was x squared. Find my original equation. X squared plus 2. I don't want to make any mistakes on that part of it and confuse everybody, including me. And then I have to type the x. And then I have to tell it at what x value. And in this case, my x value was -1. Now, before I go on with this, I want to check with the 84 people and make sure that you're getting it in right. So we just look around and see what the 84 folks are. Okay. Family number 8. Okay, now you're going to have to type your x right there. Your x comes first, and then whatever your function is, x squared plus 2. And then that value is -1, the point you want to find that derivative value. Yeah, that slide is in there too. We've got PowerPoint. Let me find that slide. Because I think that'll help everybody see what you're supposed to have.
32.
Slide 32. Because I can come back to the others. Here you go. So if you got the TI-83, this is what you need. If you got the TI-84, it looks like this. Now mine's got x squared, because that's the one that I was using. You want to do x squared plus 2.
Mine's not.
Mine's an 84, but it's doing the.
Yeah, some of the 84s are the same and some aren't. Okay, yeah. If it acts like, if it doesn't bring you up that little funny looking stuff on the yellow, then yours is just like mine. Some of the 84s are just like mine.
So I was doing what?
Yes, you type x. Oh wait, no, so, no. Yeah, no, yours should be the y1, so you're going to have x squared plus 2. Even though you could put y1 in there, I'm trying to make it simple. We're going to comma and an x. It's above the number 7. Okay, no, it's okay. So turn it back on. Hit second, enter. Oh gosh. Okay. Math back down to number 8. You can do this. Okay, x squared plus 2.
Is with the equation that's
Comma x to be. Gross was negative 1. And that's what you need for your last entry also. So the difference in yours and hers is that you put in the function, the x, the number. She has to put in the x, the function of the number. So that will kind of add to your function. Just hit secondary, you will keep the whole thing. Just take your cursor back up there inside this place.
The negative
Now put plus 2. Yeah, leave everything else the same. Well, and it would be, because the only difference between the two is where the x intercept is, so they do have the same slope. Yeah. So if you want to check that you did the arithmetic for finding the slope of the tangent at a particular x value, when you went through all that complicated arithmetic that I did up here, you can actually check it this way and make sure that you did get the right answer. And that's what some of those problems on the practice test were that I told you could mark out, because I'm not going to make you do that on this test. I know some of you are still getting used to the technology. So let me see. This is a different example, and given that we've only got about 15 minutes left, I think we can skip that second example because your show me homework doesn't reference this example, I don't think. Let me make sure. Okay, your turn 1 for 11.4 says find the equation of the secant line, which we did, through the points x equals -2 and x equals 1, and then find the equation of the tangent line at x equals -2. And then your turn 2 says, using the same function that you had in your turn 1, find the derivative, and then find the value of the derivative at f is -2. We haven't done that part yet, and that's not what the second example is. Let me make sure I hit them all. Okay, so when we finish the rest of this PowerPoint, you should be able to do all of these. So we should be good to go, and I can skip that one problem. So we'll skip this one. Because we'll be fine without it. And start from here. So find in your notes where it says definition of the derivative. Should be the top of page 29. The notation f prime of x, which is what this is, it's f with a little accent mark over it. F prime of x is read f prime of x, and the function, and for some reason it stuck an extra character in yours, the function f prime of x is called the derivative of f with respect to x. And that's why when we were doing it numerically on the calculator, you had to enter the function and then put in the x, because you were telling it to find the derivative with respect to x. Even though there weren't any other variables, it had to be that you were using that with respect to x, because in higher ordered or higher levels of calculus, you might have two variables in that function. So it needs to know which one's the independent variable, and that's what you're having to tell it, is which one is the independent variable. And if x is a value in the domain of f, and if f prime of x exists, then we say that f is differentiable, meaning that we can take the derivative, or we can calculate a difference quotient that will give us the slope of the derivative at x. And the process that produces f prime of x is called differentiation, which is why we use the word differentiable at x. There are some places on functions that are not differentiable. These are some things that I want you to make sure you understand what the distinction is between them. I may put these definitions on your rules that you'll get to use on your test, because at this point you're still trying to get things straight in your mind. So if you're trying to find something, it would help you to know, am I trying to calculate a difference quotient or am I trying to calculate a derivative? And here's the difference between them. The difference quotient itself is the slope of a secant line. You're actually still using 2 points. It's called an average rate of change, or an average velocity, or an average rate of change in cost, revenue, or profit. You have 2 points in a difference quotient. One is close to the other, but they're still 2 distinct points. When it becomes a derivative is when you take the limit of that difference quotient and let h approach 0. That's what makes it into a derivative. And that derivative is the slope of a tangent line, not a secant line. It's not an average rate of change, it is an instantaneous rate of change, a rate of change at one single point. So it's the instantaneous velocity. It's also called the marginal cost, revenue, or profit. Average rate of change is not marginal rate of change. Okay, marginal is the derivative. Average is still the difference quotient. So when you're interpreting the derivative function, here's some things that you want to remember. The function f prime of x represents the instantaneous rate of change of y equals f of x with respect to x. It can be interpreted as marginal cost, revenue, or profit if the original function represented cost, revenue, or profit. And from now on, we're going to use the rate of change to mean instantaneous rate of change. Because we're not always going to have straight lines, we're going to have curves, and in order to talk about marginal change, you have to be able to talk about the slope of a curve. The function f prime of x represents the slope of the graph of f of x at any point x on that graph. So if the derivative is evaluated at the point x equals a, then it represents the slope of the curve or the slope of the tangent line, because those are equal at that point where x is equal to a. So for example, find the derivative of f of x equals x squared. And then we're going to calculate and interpret f prime of 3. And again, I'm going to switch over here to the notes and work through this one with you step by step rather than just showing you on the computer. And at this point, the calculator isn't going to help much till the very end. This is what we've been doing, but I'm breaking it down into steps because we don't have a value for x to plug in. We're actually just going to do algebra with x as the variable. So we don't have a number to plug in. This is our function. Find the derivative means to apply what we call the 4-step process. The first step of the 4-step process is to find f of x plus h, which means we simply replace x with x plus h. Okay? If we expand f of x plus h, we get x squared plus 2xh plus h squared. And I've left out the f, but you're supposed to be finding f of x plus h minus f of x in the next step. So the next step, we're going to take the result from the last step, and we're going to subtract f of x, which is what we started out with. And when we simplify that, what happens is the x squareds drop out, and all we have left is 2x plus h squared. So we're going to take the result that we got in the last step in step 3, and we're going to divide it by h.
Isn't it 2xh?
Yes, it is. It is xh. Thank you. I lost it after the first step. But yeah, it's still there. It has to be. And I'd be sitting here scratching my head in a minute if you hadn't said that. So now I'm going to divide it by h. But that presents me with a little bit of a problem because I can simplify it. So I'm going to factor out the h, which leaves me with 2x plus 1h still, divided by h, and my h's are going to cancel. So now that I've got just 2x plus h left, I want to take the limit as h approaches 0, which means basically that's going to disappear. And the limit then is 2x. The difference now is we didn't wind up with a number, we wound up with a formula. This is the formula for the slope of that curve at any x value that you want to find it for. So for example, if I want f prime of 3, then f prime of x is equal to 2x. Therefore, f prime of 3 is equal to 2 times 3, which is 6. And what we've done is the slope of the tangent line to the function f of x equals x squared, which is this curve, at the point where x is equal to 3, which means the y value is 9. At that point, the slope of the tangent line is 6. Which means the slope of the curve at x equals 3 is 6. Okay? Now that's very similar to what we did in the last section, except now we've still got a variable left because it's now a formula. We're not finding it for a particular x value. We're finding it for any x value we would ever want to use. Okay? You can find the derivative. This explains how to find it for any particular place on the function. You can find it using your graphing calculator if you'll follow through these rules. But for the most part, you're going to need to be, you don't have to learn how to do that right now. What you want to do is you want to learn how to do what I just showed you. So that's all explained out step by step in the PowerPoint. This is explaining how to do it on the calculator to make sure you did it right. And this is the slide we already looked at. So this is just a summary of the rules for finding f prime of x from the definition, and I will probably put that on your formula sheet. So equivalent expressions for saying the change in x is x2 minus x1, or b minus a, or delta x, or h, which is a way to write delta x with just one symbol, the change in the x values. This one works the same way. 4 over x, if you find f of x plus h, it becomes 4 over x plus h. And when you take 4 over x plus h minus 4 over x, you have to get a common denominator. And then collect like terms in your numerator and reduce it down and factor out or cancel out what you can. And then you have to divide it by h, but the trick here is, since you've got fractions, it's easier, if you're going to divide it by h over 1, what you're really going to do is you're going to multiply it by 1 over h, which means there's that h back in the denominator again. So that turns out to be, the h's actually will cancel, and you wind up with negative 4 over x times x plus h, and you want to let h approach 0. But in this case, if you let h approach 0, x times x is x squared, and the negative 4 doesn't change. So there's your derivative formula. That's actually what that one is. And I'll give you, if the PowerPoint's not already in D2L, I think it is, but if it's not, I'll put the PowerPoint in there so you can fill in your notes. This is just an application of the same thing. You find the derivative and you use x equals 100. This is the part that I want to make sure that I show you, though, because this is important. If the limit used to define the derivative doesn't exist, then the derivative's not going to exist. A derivative can exist in two cases. It can exist in a point where the function is itself not defined. So, for example, f of x equals 4 over x. There was no tangent line where x is equal to 0 because f of 0 is not defined. So you couldn't calculate a tangent at x equals 0. There's no way, there's no point to connect to. Derivatives also don't exist at corners or sharp points on a graph. For example, an absolute value function I'm showing you here, there is no derivative at x equals 0 on this function. And the reason there's not is because if you actually do the derivative, it winds up being the absolute value of 0 over 0, and that's not defined either. And that only happens at a sharp point, by the way. Now, that's why you have to be careful and why I'm not really pushing you to use the nderiv command, because sometimes it'll give you a numerical derivative for an x value that it shouldn't give you one for. Because it's not looking at things from an algebra standpoint, it's just doing arithmetic and it thinks it's fine. So the slide I want you to look at, you cannot do a derivative at sharp points, so there's no tangent line possible here or here. There is no tangent line here because the derivative itself doesn't exist, because the left and the right don't meet. Same thing here, you can't approach infinity on both sides because infinity doesn't just magically come together. There's always going to be a little distance between those two, and that's because there's an asymptote at that point. You can't take a derivative at a vertical tangent. And in this case, this might be where you have a cubic function or something. You can't draw a derivative and have it be vertical. And the reason that you can is because while it does come together, the slope of a vertical line is undefined. So the tangent line is going to be undefined at that point. And the function's not defined at x sub 6, but you could find a tangent line there. The only problem is it can't be through that point because the function doesn't have a point there. So you could say it doesn't really, while you can calculate it, it doesn't do you any good. It doesn't tell you anything. Okay? Because the function's not defined there. Those are the things that you need to remember for the test. And I summarized all of those, and there again, I may just give you those on a formula sheet on this first test. And then you'll just need to know when to apply them. Okay? You have your practice test. I will put the worked out key out there for you. Probably by Wednesday. I should have time to get it done by Wednesday, so that you'll have it. First thing you do before you worry about doing your homework is you please try to do those show me problems so that if you're in trouble on any of them, that I can give you feedback on them before you go attempting to do your MyStatLab problems. You should be able to do your show me problems from your notes. Okay? Anybody has any questions, text me, ask me, post them on Show Me, then text me so I'll know to go look on Show Me. And I will see you next week. If for some reason, and I'm not seeing the weather forecast, but if for some reason it snows next week, we'll just do it the next week. You'll have longer to study. Yeah. Even though I told y'all to mark out some of those problems, I probably put the answers to them out there with everything else.